Okay, I'll start again. Okay. Uh, Good evening, Alfred. Can you hear us?
Yes, I can hear you now.
Okay, perfect. All right. So I wanted to thank you for your time, Alfred, today. We have quite a few people at the University of Toronto, Mississauga campus wanting and listening to your talk. This meeting is being recorded so that folks who couldn't make it today are still able to enjoy your presentation. I wanted to welcome everybody and to this meeting today. Like I said, Dr. Alfred Ng is joining us from Montreal, the Canadian Space Agency. On a very personal note, Dr. Alfred and my father had the same professor at University of British Columbia, so both did space technology research, and that's how we are connected. So it's on a very personal note there. With that said, Alfred got his PhD from the University of British Columbia in 1992. He joined the Canadian Space Agency as a research scientist the same year, and he's currently the Deputy Director in the Engineering and Capability Demonstration Directorate. He served for 6 years as the chair of International Astronautical Federation Astrodynamics Committee. He is also a member of the International Academy of Astronautics. Currently, he's managing the Stratospheric Balloon Program, and he is also the technical lead of the Canadian CubeSat program. He has authored and co-authored 14 journal publications and over 45 conference papers. As I mentioned, our speaker joins us from Montreal, the Canadian Space Agency today, and we are privileged to hear from him on understanding the Lunar Gateway orbit. With that, welcome, and over to you.
Thank you. Thank you for your kind introduction. And once again, thank you for this invitation. I've never done this kind of lecture, okay? So I'm trying my best, okay? Bear with me if there's any technical issue here. So today I want to talk to you about the subject, understanding lunar gateway orbit. I find very fascinating. So I hope you share my enthusiasm why you find fascinating. I am trying my best not to introduce any equation throughout, but except there's one equation that I cannot remove it. So bear with me. If you don't want to listen to the equation, just close your eye. I'll skip through it, okay? So let's start. So as you all know about right now, we have International Space Station, okay? It is orbiting around the Earth, about 350 kilometers above us. It was started construction in 1998 and fully constructed in 2011. And it has been fully occupied by astronauts continuously since year 2000. However, the current plan is that by 2030, NASA plans to decommission the space station. Okay, instead, it will be deorbited, and then it will, hopefully by that time there'll be commercial space station to be launched and built by that time. So why NASA is doing this then? The whole point is that for them, they say, okay, now going to space station become so routine, regular operation. This should not be the job for NASA. NASA should look for the next frontier, which is, let's say, go to the moon. So this is the whole idea why they say that we have to decommission space station so that they can save the money to invest in the future lunar gateway. Okay, so this is the latest, the plan for the lunar gateway in the future. It will be much smaller than the International Space Station. Right now, the International Space Station has a dimension. They always say that it's the dimension of a American football field. Okay, it's 100 yards end to end, and then I think it's about 30 yards from one side to the other. But the future one will be much smaller. It's just a different module contributing from the same partner except Russia. Right now, in the Lunar Gateway, they don't plan that the Russia as the partner. Okay, and Canada once again will contribute a future robotic arm for the gateway. Again, it will be a smaller robotic arm. So what is the whole point of the Lunar Gateway? It will be providing like two main objectives, saying that it will be provide essential support for long-term human return to the moon surface. Okay, basically, this Lunar Gateway will be orbiting around the moon in such a way that the future astronaut can go to the lunar surface easily and come back to the station when necessary. Okay. And second point mentioned, like in the, if you go to NASA website, you can see that it will serve as a staging point for deep space exploration. So in this topic, I'm going to explain to you how they select this lunar orbit, okay, this orbit for the future gateway. It turns out to be not a very straightforward task, okay? And also, I'll try to explain to you what does that mean by the second point, staging point for deep space exploration, okay? To do that, I have to go back to some kind of basics, okay? Because I think it's very fundamental. If you understand some kind of basic concept about like the orbit, then you appreciate the choice for the Lunar Gateway orbit. So here I will try to go through like the basics of Kepler's law. Yeah, you probably heard about the Kepler, Johannes Kepler, but I just go through why this is significant. And then also try to go through here the understanding the launcher and what's the meaning of delta V. Okay, I'm sure if you watch some sci-fi movie, you probably heard of this term delta V before. I still remember when I watched a movie like The Martian. Okay, the word delta V mentioned quite a few times in the movie. So I will explain to you why this is such an important parameter. What does that mean? And then I'll talk about what we call the Lagrangian orbits. Okay, this again a very fascinating subject. And finally, I'll talk about the low energy transfer. Okay, this is kind of like the breakthrough in the late 80s. Okay, about how we design the orbit. Then after introducing you with all this concept, then I'll explain to you, then you understand why we chose the future Lunar Gateway orbit in such an interesting way. So just to recap, if you have never heard of like Kepler, why we think it's significant is that because in the early civilization, in the human civilization, at the beginning, we all believe that the Earth is at the center of the universe. Okay, they believe in God. So they believe if there's God create human, that means that God must put us at the center of the universe. This was a thinking for thousands of years. Nobody challenged until at the beginning it was like Nicolas Copernicus. He believed this is not right. Okay, we are not at the center of the universe. But he did not want to openly say it out loud because he is a priest by profession. So at that time, the Catholic Church also, like the teacher of the Catholic Church also said that like the Earth is at the center of the universe. So he dare not to say it now. Then after Nicolas Copernicus passed away, then Galileo Galilei, he discovered some of the writing by Nicolas Copernicus. And again, he said, yeah, he's right. Nicolas Copernicus is correct that we are not at the center of the universe, rather the sun should be. However, because he spoke out, so Galileo Galilei, he was punished by the Pope, and he was like sentenced to have a life sentence that he cannot leave his house until he died. Then around the same time, there's also a very famous astronomer called Tycho Brahe, a Danish astronomer, and he has been observing like collecting the measurement of like the planets. Okay, those are planets that you can watch by naked eye. The Mars, Venus, Mercury, Jupiter, and Saturn. Okay, he had been doing very precise measurement of all these planets, and he kind of believed that Nicolas Copernicus is correct. But he just said that from his measurement, there's something he could not figure out what not quite right. Okay, he in his mind, he said, yeah, okay, maybe we are really, the sun is the center of the universe, but why the orbit going around the sun, he figured that does not look like a circle. So he could not figure out what's happening. So this is why he invited Johannes Kepler to look at his the observation, to go through all his I believe he had more than 27 years of observation. He kept it very meticulously. So Johannes Kepler went to his observatory and looked at his data, go through his light measurement, and finally took him about 5 years time, and he discovered what happened. And he formulated this into 3 laws. This is what we call the Kepler's law. So the first law, what Kepler is saying is that all the planets are going around the sun in an ellipse, not a circle. Okay, not really a circle. So this is why it stumbled Tycho Brahe, he was stumbled because he thought everything should be circle. Okay, but Kepler said no, everything is going around the sun as an ellipse. Then here I just want to introduce the concept of an ellipse here, okay? Because later on I have to explain something with this one. When we have an ellipse, so you have 2 sides. The longer side we call the major axis. The shorter side we call the minor axis. So semi-major axis is basically half the length of the major axis, okay? So this term, we use it very often when we talk about the orbit. So bear with me, okay? Keep this in mind, semi-major axis refer to half the size of an orbit. Then the other property about ellipse is that we have a parameter we call the eccentricity to describe the shape of an ellipse, okay? If it is a circle, we call that it has an eccentricity. Here, for example, I have a ring which is circle. Then we say it has an eccentricity of 0. Then you can imagine if we have a circle, if I start squeezing it, then the number E will start going to gradually increase. Okay, it will gradually, the bigger it is, then that means that it will become a fatter ellipse. Okay, so when it is basically it will be E will go between 0 to 1. Okay, when you reach 1, that means you're squeezing so much, then the orbit will break open. That means that it becomes a parabolic orbit. It means an open end here. But if it's a circle, it's a closed orbit, it will be always between 0 and 1. This is the eccentricity parameter. Okay. Now that I talk about the ellipse, there's the 0 to eccentricity factor. And I also want to introduce you the term, probably you are astronomer, you have heard this term before, okay? Basically, in the ellipse, when all the planetary object doing the planetary motion around the sun, so we say the sun is the focus for the ellipse. So when the object is closest to this focus, this point we call it periapsis. When the orbiting object is farthest away from this focus, we call apoapsis. Okay. So in the case of the Earth, so here we are talking what? We are talking about satellite. Okay, satellite will be orbiting around the Earth. Then means that in the case of the Earth, then the closest point when we launch a satellite, okay, in the orbit in the space, the closest point we call perigee. The farthest point we call apogee. Okay, and then in the case of the moon, the closest point. So basically, when you launch an object into the moon lunar orbit, the closest point we will call it perilune, and the farthest point we call apolune. Likewise, for the sun, we will say that the closest point, okay, for a planet going around the sun, the closest point in its orbit, we call it perihelion. And the farthest one we call aphelion, okay, missing the O, okay, we just got aphelion, okay. Why I introduce this term is because when I describe the lunar orbit, it will come back this term, perilune and apolune. So that's why I want to introduce you this term. Here I just show you the table that you can find in astronomy almanac, okay, showing for all the major planets around the sun, what are the eccentricity. So what are the mean distance? So mean distance here basically is the semi-major axis, okay? So we use like the sun and earth's distance as a reference. We say this is 1 astronomical unit. So that means this is the semi-major axis between the sun and the earth. We call 1 astronomical unit, which is roughly about 150 million kilometers. Okay. And here, then I show you like when the earth is closest to the sun. So at the perihelion is about 0.98 astronomical unit, and the farthest one is 1.02 astronomical unit. So here you can see this, the difference. When the earth is closest to the sun, and when the earth is farthest from the sun, there's about 6 million kilometer difference here. Okay. Likewise, for the other planet, you can see this depending on the eccentricity, then the difference will be changing. As you can imagine, the bigger the eccentricity, then the ratio of change in terms of the difference of the distance will be the larger. Okay. Okay, so after introducing the Kepler first law, now I want to also introduce you the Kepler second law. What Kepler observes is that when a planetary body orbiting around the sun, as it's getting closer to the sun, it seems to be moving faster and faster. And then when it is going away from the sun, it goes slower and slower. However, what he found that at any instant, the area swept through is always the same. Okay, that means that when it is farther away from the sun, okay, so the distance is longer, so the area it grows slower. So that this area swept through at equal time will be like the equal time will sweep up the equal area. So this is what is known as the area law. The time taken by a planet to reach a particular position is represented by the area swept out by the radius vector drawn from the fixed sun. And you say that the equal time, equal area, this is the whole point what Kepler discovered. So based on this, you can imagine this is why when a planet going around the sun, the closer it is, the faster it goes. The farther away, the slower it will be. So here I just repeat what I just said here. What Kepler discovered saying that, for example, in this case, when the planet traveling from the A to B, it swept out an area represented by here, A, B, and F. So you say if this area is same as this area, which is like when it is at the aphelion, so it go from C to D. If this area is same as this area, that means the time to travel from A to B is same as the time travel from C to D. Okay, so this is law also applied for every planetary object, including planet. For example, here I show you, okay, based on like the Halley comet in 2015, it is at the position around the aphelion. Okay, it is almost at the farthest point from the sun. Then in 2017, 2 years later, it looks like it barely moved. Okay. Now, by 2059, it's to start getting very close to the sun now. It is like 2059 is on this side of the sun. Then by 2060, it is really close to the sun. And by 2061, it's already on the other side of the sun. So you can imagine that. So that means that when it is here, it is going very, very slow. And once it's getting close, it is going very, very fast. Okay, so this is the Kepler second law. The third law is, we also call it harmonic law. So what Kepler discovered is that the time for an object to go around the sun, okay, is proportional to the semi-major axis. So this is why I have to introduce you the concept of semi-major axis, okay? You say it is really proportional to the semi-major axis in a way such that the square of the period is proportional to the semi-major axis, the cube, okay? So what does that mean? That means, for example, if you have a planet which is a semi-major axis from the sun, which is a distance A, then it has a period of T, or so like say 100 days around the sun. Then you figure, okay, if this distance is double, then the period is not 200 days, rather it become the 2 to the power 3, and then you take the square root, which will become a 2.82 time. Okay, that means that when you double the distance from the sun, the period will become like 2.82 times larger, not just double. That explains also to you that why Mars, which is only 52% from the sun, the Martian year is 88% longer. Okay, it's not like 52% longer, it is 88% longer. Okay, so these are the 3 laws of Kepler. What is interesting about this semi-major acid is that what Kepler is saying that this period is proportional to semi-major acids. So that means that it does not matter whether it is a circle, ellipse, okay? So what I'm drawing here, all these objects, they all have the same period around the sun. If we have a fictitious like planetary body around the sun, if they all have the same semi-major acids, they all have the same period around the sun. Okay, this principle is also, remember, all these Kepler's law apply to the planetary bodies, but also apply to all the artificial objects. That means that all the satellites we launch around the Earth all obey Kepler's law. Okay, and another point to keep in mind is that all the like the planetary body or artificial satellite, when they're operating around the sun or around the Earth, they are going in a planar motion. Okay, the object will just go into the plane. Okay, so this is a very important concept when I talk about the lunar orbit. You see the big difference here. Right now, you just keep in mind that all the satellites around the Earth, they are all going in a plane. So the other one more concept I want to introduce here is that when we put that, when there's a like all the operating objects, they are actually going at a very high speed. Okay, not only that, they are at a distance from the center body. Okay, for example, in the case of the like the Earth from the sun, okay, it has a like distance of 1 astronomical year away. So that means that at any time, there are 2 energy possessed by the Earth going around the sun. One is the kinetic energy, which is like due to the motion. Okay, remember when I talk about like the Kepler's second law, when it is going around when it is at the perihelion, it is going very fast. That means the kinetic energy at that moment is very high. However, at that moment, it is so close to the sun, the potential energy is low. So the sum of the kinetic energy plus the potential energy is always constant. So this is the interesting part about the energy does not change. If you like, when you all the orbiting object around the sun, the energy hardly change. Okay, because they just have been doing that for like billions of years. The energy does not change. The reason is because like there's always conservation of energy. When they close to the sun, it goes fast, but then the potential energy is low. But when it's away from the sun, the potential energy is high, but then it is going slow. So the kinetic energy is low. The sum together is always constant. So we can extend a similar argument to satellite operating around the Earth. Okay, with one exception is that there will be some kind of when we launch a satellite around the Earth, there's some disturbance due to like the Earth atmosphere. Okay, the Earth is not like true vacuum. At the low altitude, there's still some kind of like the air particle which serve as some kind of drag force to the satellite. And there are also other kind of like force that will kind of like disturb the satellite around the Earth. So for objects near the Earth, they don't really, they would kind of like would lose some energy, but otherwise they are still following the same rule, like the kinetic energy plus potential energy always constant. So here I show you like, for example, at the sea level, if we want to launch an object into space, it has to be launched at the 7.91 kilometer per second. As you go higher, okay, then the orbital speed will be lower, okay, at 300 kilometer per second, the orbital speed must be 7.72 kilometer per second, and the 600 will be 7.58, and GEO will be 3.07 kilometer per second. So then you may say, figure, oh, does it mean that it takes less energy to go up there? No. The reason is, as I mentioned, the higher you are, then you have the higher requirement for the potential energy. So such that even though here it looks like it is going slower, but the potential energy is much, much higher. So that means that the farther away you're from the Earth, the more energy it takes to go there. Okay, the lower you are from the Earth, the less energy required. So when we talk about energy, if we convert this number, okay, into like the energy of the orbit for the, right, it will come up to some funny number. You can see that it will come up to be like minus 62.6 megajoule per kilogram, minus 29.8 megajoule per kilogram at 300 kilometer, and then minus 28.6, okay? So I am not going to, as I promise you, I'm not going to go into the math, but I just want you to appreciate this number is very hard to understand. Okay, for the person, it's really hard to understand. So this is the kind of like driving force for us to come up with a better number to explain the energy related to the orbit, which I will introduce when I talk about the delta V. Okay. Now I'll move on to the next subject, which is explain like the launcher. Okay, because I have to introduce subject of launcher so that I can introduce the subject of the delta V. Then things will start coming gel together. You understand, okay, when you put something in the space, it take energy and take the delta V, okay? So what is really a launcher? Basically, you can look at it as a like big container of kerosene, right, with liquid oxygen as an oxidizer. So it is a big, big container of chemical energy. When you light up the rocket, so basically they're converting the chemical energy into a big force that will push the rocket into space, okay? So basically they're converting the chemical energy into kinetic energy, basically give it the speed, and then also potential energy so that it can lift the Earth gravity, okay? So as I showed in the last figure, right, to put an object into like 300 kilometer orbit, it has to be 7.72 kilometer per second. So this is why the rocket will be fast enough push the object up to that speed and also at the altitude of 300 kilometers such that it can be placed into the orbit. So then when you go up to from the surface of the Earth to space, there's a lot of air, so it causes like friction. So this is why we decided the rocket to be really aerodynamic, so that it will minimize the drag and so that it can easier to gain speed and bring it into space. So essentially, you can look at it, the rocket is basically like give a taxi ride for your satellite, okay? So it is burning all this, converting all this chemical energy into like kinetic and potential energy such that you can put your object into space. So here I'll introduce, this is as I'm, okay, not this slide, the next slide, then I'll introduce the rocket equation, okay? But basically, the way rocket equation, very simplified rocket equation here is based on Newton's law, okay? When you burn the fuel, okay, the fuel is burning, so then the exhaust, it is exhausting high speed. So this is represented by, we call the V exhaust. And then you're burning the fuel like certain like kilogram per second. So this is represented by m dot, okay, the rate of the fuel being burned, and then also the exhaust velocity. So together, this is the momentum in the downward position. When you light up the rocket, you can see with the fire, the flame, it is going very high speed. So it generates the momentum. So this momentum, according to the Newton's third law, it will kind of like because this is action, it generates reaction onto the rocket. So it generates the momentum in the opposite direction. So this is what it is pushing up, pushing the object up into the air. As it go up, then there's a gravity. So the gravity is trying to resist it going up. So that means that there's a drag, like the gravity is represent a force, trying to slow it down, okay? So that means the rocket as a minimum, it has to overcome this gravity force. Then whatever the difference between here and here, this is what is like the resultant extra momentum. This is giving the rocket the acceleration, okay, the mass of the rocket times the delta V, which is the represent the change of speed, okay, is due to the momentum from the exhaust overcoming the gravity force, and this is the net momentum going upward and pushing the rocket into space. Okay, so this is the only equation I introduced today. Okay, so I just want to repeat what I am saying. So basically, when you turn on the rocket, it start burning fuel, okay, and then it will be like going like, for example, like say 10 kilograms per second, and then exhaust speed like maybe like 300 kilometers per second, something like this. Okay, so this is like the momentum coming up, and then the negative of this would be the momentum pushing the rocket upward. But as it goes upward, because of the gravity, okay, the gravity trying to hold it back on Earth, but it has to overcome it. So the net momentum here is what is driving the speed change, okay? So this is a very simplified rocket equation, but at least you appreciate two things. One, the exhaust velocity is very important for the rocket performance, okay? You can see this. The bigger this exhaust velocity, the better it will be. The second thing here is the gravity, okay? So gravity here times the time. So that means that the longer it takes, that means that you are wasting more energy, overcome the gravity. So this is also the reason why when you design a rocket, you try to escape the Earth in the shortest time possible. You don't want the rocket go slowly up, because this delta T, the longer it takes to go into space, the more energy you're wasting. So this is why we make the rocket as powerful as we can. So what is interesting here, the simplified equation tell us something. Basically, it said that everything we are doing here at the end of the day is resulting in the change of speed, the delta V. Okay, so all the rocket is doing is just changing the speed, delta V. Okay, so this is why we introduced this concept. Delta V is a concept. It's easy to understand. Okay, all this energy term I introduced earlier, megajoule per kilogram, it is hard to understand. And with delta V, you understand, okay, that means the change of speed, okay, you understand the change of speed meaning like meter per second or kilometer per second. It is a physical parameter that you can appreciate, you can understand better. Okay, so this is why we use delta V when we describe orbital mechanics. This term is used so often, okay, in describing the rocket performance, in describing when we move the space object from one point to another one. It is all about changing the velocity, and this is make things much easier to understand. Okay, so delta V is basically a measure of the amount of effort that is needed to change from one trajectory to another. Okay, so it could be like from Earth to space. You can say that this can be measured by delta V. And then when you're in space, when you in one orbit, you want to go to another one, you can say, okay, this is how much delta V require. So it is much easier to understand. Okay. And further, how we use it now. So basically we say, okay, if I calculate quickly, okay, so delta V, I don't know, maybe like 1 kilometer per second. Then I say that, okay, I know, for example, I know what is the propellant I'm using. And I know that how heavy is my satellite. Then right away, there's some equation we can plug in and click, oh, that means I have to carry how much the propellant mass, okay, how much fuel I have to carry to give me this kind of delta V, okay? This is a very simple way for us at least to get some idea, what do we want to do, whether this is feasible or not feasible, okay? I'll give you an example here. There's a Horizon mission going to the Pluto. I think you remember this is like the NASA and John Hopkins Horizon mission. And if you remember, when they arrive at Pluto, basically it just zoomed by. Okay, after traveling 7 years, it just zoomed by. Like kind of like say hi and bye. Okay, it did not slow down at all. People always ask me why we do that. Why we spend 7 years to send a probe all the way to Pluto, and we don't slow down and take a picture or go into like the Pluto orbit? Why? The reason is driven by delta V. Okay, so Horizon, when it arrived at Pluto, it was traveling at this speed, 16.26 kilometers per second. Okay, and Pluto is such a small, well, we don't call it planet anymore. Okay, so small object that if it wanted to go into the Pluto orbit, it has to slow down to 0.8 kilometers per second. Okay, so now you're going from 16.26 down to 0.8 kilometers per second. Now imagine this is a satellite, so there's no brake. Okay, where's the brake come from? The brake is coming from burning, like the burning fuel in the opposite direction to slow it down, right? So this is why it is like the delta V. So that means that, okay, if I want to go from this speed to this speed, that means I need a delta V of 15.5 kilometers per second. I'm telling you, this is a lot. 15.5 kilometers per second is a lot delta V. In this case, for example, the Horizon is a satellite of 400 kilograms. If you want a 15.5 kilometers per second delta V, the satellite actually have to carry 28 tons of fuel, which is just not possible. Okay, so it is for this reason you can do a quick calculation and say, no, it is impossible. If we want to go to Pluto in 7 years, it's just not possible to carry the fuel so that it can become an orbiter. So this is why Pluto is a flyby mission. It's not an orbiter. Okay, so this tells you like the delta V is a very useful parameter as a like first cut to say, okay, when I want to do this, is it feasible or not? So it is a very good parameter and easy to understand. Okay. Of course, if you like one day you say that I have like some kind of better fuel system, or I can like do like better trajectory planning, that I can reduce the delta V. Even though you say you reduce it by 10% delta V, it still take you like 17 tons of fuel. So this is why it's just not feasible to do it as an orbiter. Okay. So now I introduce like you two things now, like the Kepler orbit, the launcher, explaining the principle launcher, and also explain to you like what's delta V. The next thing I want to talk about is called Lagrangian point. Okay. So basically, actually, it's not Lagrange himself that discovered the Lagrangian point. Rather, it was another mathematician called Leonard Euler. Okay, but for us, we just call it, all the credit go to Lagrange, and we call it Lagrange point. So what they have postulated is saying that, for example, between the sun and the earth. They postulate that there are points in which the pull from the sun and the pull from the earth will balance each other. Okay? In principle, they said that in principle, if you put an object there, it has equal pull from both the sun and the earth, it should just stay there. Okay, it's just stay there. So when the earth go around the sun, this object will go continuously follow. Okay, because like it is just at the point where the pull from the sun and the earth just balance each other. Okay, so this is what they call Lagrange point. And they said that actually there are 5 of these Lagrangian points. The first one, which we always call L1, is the Lagrangian point between the sun and the earth. And then L2 will be on the far side of the earth. We call L2, okay, which is each one is roughly about 1.5 million kilometers from the earth. Okay, Lagrangian point between the sun and the earth is about 1.5 million kilometers. And then they postulate there's also another Lagrangian point called L3. This is a point on the far side of the sun. No one has ever seen it. No one has ever seen any object there. So it is kind of like in principle it should exist, but no one can ever prove it was out there. Okay, L3 is I heard that there are many sci-fi fiction talk about L3. So if you come across sci-fi fiction called so L3, you know what does that mean here. And then there are the other 2 Lagrangian points called L4 and L5. Okay, this is like at the distance roughly about 150 million kilometers from the earth. So it's kind of like the equal distance between the sun and the earth. Okay, except it is on the path between the earth trajectory around the sun. Okay, it's called L4 and L5. So Lagrangian point exists between any 2 planetary objects. Okay, well, 2 planetary objects around with the sun. Okay, so that means that this one L1, L2, L3, L4, L5 is between the sun and the earth. And do they exist? L4, L5? Indeed. Okay, as I mentioned, L3, whether it exists, remain not proven. Okay, it just in principle they should be there, but no one can really ever prove it because on the far side of the sun, we cannot go that far to see. However, L4 and L5 have been proven to exist through the Sun-Jupiter Lagrangian point. Okay, here the astronomers discovered there's a Trojan asteroid belt. Okay, so they noticed that there are many asteroids. They look like they are trapped around the L4, L5. So this is why we know that yes, Lagrangian point L4, L5 exists. Okay. So knowing that Lagrange point is such an interesting point where the force between the sun and the earth balance each other, that means that if we can put somewhere like the artificial satellite there, that will look interesting, right? So this is exactly what we call the Lagrangian point mission. Okay. For example, as I mentioned, at the Lagrangian point 1, L1, if you launch an object there, so it looks like it will be always observing the sun. As the earth going around the sun, the object will be always there observing the sun. So this is what we call like the Lagrangian point orbit, L1 orbit. Keep in mind here now, even though in principle it is just a point, it turned out that when we do all this like mission design analysis, the object would not stay at that single point. Rather, because now you can imagine now, it is under the pull from 2 objects. The satellite when you launch there, it is under the pull from the sun and the earth at the same time. It will no longer stay in like, as I will explain to before, it will not stay in like the planar motion. Okay, when you launch an object there, it will be in like a three-dimensional orbital motion. This is the biggest difference from the Keplerian orbit, which I explained earlier, in which is always in a plane. The object will always go in a plane. It will never go outside the plane. Whereas when we talk about the Lagrangian point mission, because it's under the pull from two objects, they don't stay in the same spot. Rather, it is kind of hovering around the Lagrangian point in a three-dimensional way. Okay, so this is a very interesting property when we talk about the Lagrangian point. For example, James Webb. Okay, you all know about James Webb. Okay, so James Webb was sent to Sun-Earth Lagrangian point 2. Okay, in simple reserve, many times we write like SEL2. Okay, it was sent in the Sun-Earth Lagrangian point 2 orbit. Okay, why is that so? Because the astronomers said that, oh, we are some thermally sensitive instrument. They cannot be hit by the Earth and by the Sun. Okay, that means that they rule out the possibility to launch the object around the Earth. They said, no, if you launch it around the Earth, no, this is not good. Okay, so then they said the only way is that if we put this satellite in the Lagrangian point 2, so this is kind of like you are using the Earth in between as some kind of shield from the direct hitting from the Sun. Okay, at least it is always pointing in the darkness too. So this is why it was selected using the Sun-Earth Lagrangian point 2 orbit. And also interesting here that when they send if you remember, when they launched the James Webb, it took almost a month when it arrived at the Lagrangian point 2. Okay, so the reason for this is that when they send it to like in the space, they want to go to Lagrangian point, they try to find a way to minimize the energy to arrive there. Okay, even though you say, okay, once they launch into space, so you don't need to do anything, right? There's no friction, so it should continue to go there. Yes, it will continue to go there, but once you reach that distance, you also will try to find a way to slow it down so that it will automatically go into the Lagrangian point orbit there. So this slowdown process turned out to be another interesting subject, which is we call the invariant manifold or low energy transfer. Okay, so this is I just will briefly touch upon, but here now I try to introduce the subject here. When they launched the James Webb, basically it will go into some kind of invariant manifold, so that when the James Webb arrived at the Lagrangian point, basically it will be arriving there at the right speed. It was automatically slow down in the right speed, so that it will be insert into the Sun-Earth Lagrangian point to orbit, like with the minimum energy. Again, everything we are doing here is talking about delta V. Okay, why we want to do that? Because it had carry very limited amount of fuel. Okay, so we want to carry there's a limit of fuel we can carry on the James Webb. So the longer we can burn the fuel, that means the James Webb will be in orbit for a longer period of time to give the more data, right? So everything is here dictated by delta V. Okay. Now you understand why the delta V is very important. Okay, it is like the driver for every space mission. You can say that. Okay. This is an animation explaining how James Webb arrived from the Earth to Lagrangian point 2. So this is the Earth here. Okay, and you can see this animation. So basically, it is like the path it is taken is not like go straight forward. Rather, it is following something because, as I mentioned here, is the invariant manifold, which is take the minimum energy, kind of like the minimum energy, such that once they arrive at around the Lagrangian point, it will slow down at the right speed so that it can be captured around Lagrangian point and go into this Lagrangian point orbit. So I already introduced this idea of like the low energy transfer, the manifold, the invariant manifold. where is this concept come from? It come from here. This is the mission that brought this concept into life. Okay. In 1990, Japan, the ISIS, which is the Institute of Space and Astronautical Science, launched a lunar orbiter, okay, called MUSIS A and MUSIS B, okay. This is a mothership and the daughter satellite. You can see that there's a mother satellite and a daughter satellite. They were hoping to be the first lunar mission for Japan, and also hope to be the third country in the world to attempt a lunar mission. So the idea is that when they launch this like lunar orbiter, okay, so when the Titan arrive at around the lunar orbit, it will release the daughter satellite, and then the daughter satellite will go into the lunar orbit. This was the idea. Okay, it was supposed to release the daughter satellite so they go into the lunar orbit. However, after releasing the daughter satellite, they lost contact. They could not talk to the daughter satellite. So if they cannot talk to the daughter satellite, basically the mission is lost, right? So the whole point is that you want to release the mother satellite and daughter satellite so that the daughter satellite can communicate with the mother satellite to send the scientific data. But when you cannot communicate, so that means that this becomes useless. Okay. So then the engineer in ISIS said that, okay, now that we lost the daughter satellite, can we put the mother satellite into the lunar orbit then? So they figured that, well, let's do some kind of aero braking. So basically they said that since the satellite is not going around the Earth and the Moon in the large orbit, so if we slow down the satellite so that it has a lower altitude around the Earth, so that means the perigee is lower, then it will experience more drag. So this will, when you take about more drag, then the orbit will get smaller. Okay, so this is what we call the aero braking. Okay, you make use of the atmosphere here to slow down the satellite, such that the orbit will getting smaller. And then hopefully when you go back to the Apollo, then we just need to fire the thruster to insert the mother satellite in the lunar orbit. So they did calculation. They said, oh, no, we are missing the delta V. Again, now we understand now. Why delta V is always the driving force. They said we're missing about 100 meters per second. So basically they said that, we just don't have enough delta V to slow it, to give it a burn so it can be captured by the moon. So basically they were planning to say this is a total loss for the mission. Around the same time, there's a gentleman working in the NASA JPL, the Jet Propulsion Lab. He's a mathematician. His name is Alfred. He's a mathematician. He was doing the Galileo mission to Jupiter. He was doing some kind of trajectory design. And he found that the traditional way of doing this, the orbiter, he found this dangerous and causing dangers. Remember, as I mentioned here in this case, basically once they arrive at the orbit, you try to take a big burn, okay? Burn your thruster to slow it down so it can be captured. So likewise, when you go to Jupiter, it will be the same thing. When you go there, you turn on the thruster, slow it down so that it can be captured by the Jupiter gravity to be in the orbiter around the Jupiter. He said, this is not smart. He said that you go all the way there, wait until the last second, you turn on the thruster to burn all the fuel, to slow it down. He said, this is not a very smart way. And then since he's a mathematician, he said that there must be a better way to do it. And this is why his idea, he has to say, he's a mathematician. He said that I can do better way. But his idea was rejected by his peers in NASA, saying, oh no, you're talking something too far-fetched and impractical. So this is why they did not listen to it. Until this mission, the Titan, happened, okay? And then he said, oh, okay, hear about this JAXA problem. Then he wrote to JAXA, okay? This is back in the 1980s. He sent it by fax, saying that this is the way I propose how you can save your mission, Okay, even though you don't have enough delta V, I'm telling you how you can go insert into the lunar orbit with the remaining delta V you have. Also, so this is what we call, he called it the weak stability boundary concept, but basically he kind of discovered low energy transfer concept here. And this is the same concept we use now for, like for James Webb you saw earlier. It's the same concept. Basically, he found a way that when you slow down the satellite, then you can always try to take advantage of like the third body to help you, right? Because in this earlier thinking, we just think, okay, you want to slow down, or I only look at the moon here. So I just burn the field so that it can be captured by the moon, right? But he said, well, no, maybe there's a way to slow down by taking advantage of the Lagrangian point there. He discovered there's something interesting, some interesting property. When you send an object to Lagrangian point, there's something interesting, okay? So basically he proposed that, look, now that your object is going like between the Earth and the moon, why don't you just give a little delta V so that you can send it to the Lagrangian point, Sun-Earth Lagrangian point 1 there. He said that from his calculation, he said that when you send the object to Lagrangian point 1 there is some interesting property. You do it in his way. He said that it will slow down by itself, gradually slow by itself. Once you reach this, something he called the weak stability boundary, weak surface boundary, you slow down by itself. And then from there, you can find a way to target the moon. And then you just give it another small burn. It will target the moon and go right into the right part of the moon and being captured by the moon at the right speed. So here's the animation. Okay, look carefully what he's proposing. He said that in this case, the moon is here. Okay, the object, he said that let's send the object to all the way to 1.5 million kilometers away. Okay, and then they will do some kind of maneuver, just low energy maneuver. Then it will come back in the pathway that will be easily captured by the moon gravity. Okay, so this is a new discovery by this gentleman. Okay, he said that mathematically it worked, and we should try it. And indeed, the ISS team, they follow his idea, they try and they save the mission. So this is really open up another way of looking at orbit and open up many new concepts. Okay, so basically he said that there's some kind of low energy transfer possible between the sun and the earth, and also between the earth and the moon. Okay, there's some interesting property there when around the Lagrangian point. Okay, and this form all the basis of low cost transfer. Okay, and when we always call low cost, they say we are talking low delta V. Okay, everything is about delta V. Okay, here kind of like the way they try to explain the concept. Basically, they said that if you put the object in the right manifold, it will travel down with no energy at all. It will require no energy at all and being captured by the moon. Likewise, when it's captured by the moon, it will, if you have the right, give it another small amount of energy, it can go into another manifold which will escape from the moon easily. With really little energy, it can escape from the moon, or with really little energy, it can be captured by the moon. This is the whole point of low energy transfer. Okay, so now I'm getting close to the final part of this seminar, which is talking about going to the moon. So going to the moon is 384,000 kilometers away. However, what's challenging is that the Earth sphere influence, basically the Earth sphere influence, meaning that the Earth gravity field, okay, it can exert influence up to a distance up to 929,000 kilometers. It's almost 2.5 times further from the moon. That means that when you send the object to the moon, okay, it will be always under the also influence from the Earth gravity field. Okay, so this is the simplest way when you go to the lunar orbit is always trying to insert the elliptic orbit with the apogee and altitude reaching the moon. Then once the probe reaches the apogee, then the probe inserted by full thrusting. For example, here I show you this from the Israel mission. I believe it was 2 years ago. So once it is launched in the Earth, okay, then it will gradually increase the size of orbit by firing the thruster, gradually firing the thruster until the apogee of this orbit reaches the lunar orbit. Okay, then once you time it right when the moon passes by, then you fire the final thruster so that it will be captured by the lunar gravity and become the lunar orbiter. This figure, I discovered this figure in a very old reference in NASA, and then I redrew this, okay? It's a very good figure in the sense that it tells you, again, when you see this figure again, now you understand, oh, I understand what does that mean now, why they use the word delta V, okay? It tells you basically delta V required for each major step in going from the Earth's surface to the moon surface. What it's saying is that roughly it requires 15 kilometers per second delta V, okay? So you can imagine, so basically from Earth to the low Earth orbit, which is about 300 kilometers away, it said that the delta V required is about, this is the biggest part, which is 8.6 kilometers per second. So you say, why this is the right number? So as I mentioned earlier, the orbital speed at 300 kilometers is roughly about 7.72 kilometers per second. So that means that you are launching from the Earth's surface, the rocket was not moving at zero speed. Once it's at this speed, which is 7.72, so right off the bat, you know that, so there's a change of speed already 7 kilometers per second from Earth's surface to lunar low Earth orbit, okay? So then, of course, the actual one will be the delta V required to overcome the friction, overcome the drag, and so on. So this is why it is roughly, this is the right number to go to low Earth orbit. Then it said that, okay, once you reach the low Earth orbit, then you probably need another 3.8 kilometers per second to bring in the GSO, which is the orbit which I showed here earlier. Then you will gradually bring it to a higher orbit, okay? So this is roughly about another 3.8 kilometers per second. And then, or you can just give it a big delta V, another 4.1, then you can bring all the way to lower lunar orbiter, okay? And then finally, then you give it another 2.2 kilometers per second. This is like the delta V. Once you are in the lunar orbit, then you want to slow down your orbiter so that it can touch down the lunar surface. This will be another 2.2 kilometers per second. When you sum this up, which is about roughly 15 kilometers per second delta V, or you can do other way, going through like the bigger orbit, and then you gradually still you do the same thing, okay? At the end, you still come to the same number, about 15 kilometers per second, okay? So basically what I'm saying is that this way to do that, it takes you about 15 kilometers per second. And then for the Apollo mission, it just do it a more straightforward way. It takes also about 15 kilometers per second. Then your question is why people don't do this way? This is, of course, people love to do this way. Okay, this is the shortest time to go to the moon surface. You remember Apollo, but you have to see the rocket used for Apollo, the Saturn V. It is a huge rocket. It's a very big rocket. It has a very powerful rocket. So this is why it can have the burn really fast, give all the data you need, and so that it can because this is a manned mission. So you want to shorten the time to go there. You don't want the astronaut to spend too much time gradually go out, and it takes a month of time to reach the lunar surface. This is why they use the Saturn, which is so powerful that it can give out a big thrust, give out all the delta V in the shortest time possible, so they can reach the lunar surface in the shortest time possible. Whereas for all these commercial missions trying to go to the lunar surface, they're using like the commercial launcher in this case, which is the Falcon 9. It is powerful, but it is not powerful enough like Saturn V. So this is why it can give the thrust into a smaller amount of thrust every time. So this is why it would have to gradually raise the apogee until it reaches the lunar orbit altitude. So this is why it takes so much longer time. So during the Apollo mission, there's something interesting to discover. Like during Apollo 15 and 16, they launched two small satellites. Okay, they call the particle and field subsatellite (PFS). So PFS2 released into like 8 months later, and PFS1 crashed after only 35 days. Okay, this is it was totally like the engineer by surprise. It launched. After 35 days, it just crashed on the lunar surface. And then PFS1, like they said, why is that so? They launched in the same altitude. Why one will crash so quickly? Okay, there was the other one. The only difference is in the orbit inclination. Okay, basically, they said that, okay, both launch into the like lunar orbit. Okay, the moon is here. So they're launching into different orbit, just the inclination is different. So one crashed so quickly. So they wonder what happened. And turn out that it is due to the something we call the mass concentration. The lunar surface is not as uniform as we think. Okay, there are areas in which the gravity field is much stronger. Okay, the area much stronger. So basically, the PFS2, it will launch into the inclination that will have a very strong going through the mass con regularly, which has a very strong pull when it goes fly, and this wall it causes it to crash onto it. Okay, and then it turned out that then later we discovered that there are only 4 possibilities where you can go into the lunar orbit, 4 different kind of orbit inclination where you can go to lunar orbit, that it will stay longer. For any other inclination, it will be suffer like it was under the effect of mass core, that it will crash quickly. So that means that if you want to send a satellite to the moon, you have to prepare for large delta V. Okay, so basically the delta V is saying that when your satellite is getting lower altitude, then you fire the thruster to push it up into high altitude. So that this is what we call the station keeping. Okay. And this also explains to you why, when you say that, why there's so many lunar probes at the end of the mission, they crash on the moon surface. Why they keep on doing that? Why? The whole reason is that even though you don't do that, if you are not at this orbit inclination around the moon, it will eventually crash onto the surface of the moon, okay, due to mass con here. So I introduce all this concept again is to like prepare you to understand the choice for the lunar gateway orbit. Okay, now I introduced the concept of delta V, the low energy transfer, the mass con. Now we are gradually getting there to understand the lunar orbit, gateway orbit. So I I mentioned earlier, like the Sun-Earth Lagrangian point, they're useful. Like for the Sun-Earth Lagrangian point 1, between the Sun and the Earth, it is useful to observe the Sun. The Sun-Earth Lagrangian point 2, like the James Webb Space Telescope, they're very useful for like the astronomy mission. Okay, so likewise for the Earth-Moon Lagrangian point, okay, we have the 2 of them, like L1, L2. L1 will be between the Earth. Okay, if you have the Earth and the Moon, the L1 will be in between the 2 objects, and L2 will on the far side of the moon. Okay, so both L1, EML2, L1, EML2, we discovered they are low delta V to enter. and also low delta V to maintain the orbit. That make them much more attractive, okay, than the lunar orbiter. Okay, so this is why we start thinking, okay, if you go to lunar orbiter, you need a lot delta V to maintain the orbit because of the mass core. Then if we put the future space object in the EML1 or EML2, they look much more attractive because it takes less energy to maintain the orbit. Okay, because ultimately, when you launch the future station, you want to maintain it for a long period. You don't want to keep on transporting the fuel there so they can burn the thruster to maintain the orbit. This is why it is all driven by the choice of an orbit that will require the lowest delta V possible. Okay, so here I show you like the Earth, Moon, Lagrangian point. The L1 will be about 58,000 kilometers from the lunar surface, and L2 is about 64,000 kilometers on the far side on the moon. There's also the Earth Moon Lagrangian 4 and 5. It was accessible, and it was also once proposed as a future space colonization point. But up to now, there's nothing planned for Earth Moon Lagrangian point 4 and 5. So this is the final concept I want to introduce is the halo orbit. Okay, so now, as I mentioned earlier, in the Lagrangian point, the space object is going to like the three-dimensional motion. It's not a planar orbit anymore. It's going to like some kind of three-dimensional orbit around the Lagrangian point. So in 1971, Dr. Farquhar at NASA, he proposed that we should do a Earth Moon Lagrangian point 2 station to support Apollo mission, namely Apollo 18. He said that we should launch an object there to support an Apollo 18. And he said that if we launch an object in the Lagrangian point 2, okay, and then this object will be orbiting around the Lagrangian point 2. And then from the Earth, if you look at it, it will look like there's a ring going around the moon. So that's why he said it looks like a halo around the moon. And he called it the halo orbit. So this is the point, the meaning of halo orbit. He said that because it will look like there'll be a future space object will be kind of like going a ring around the moon. He proposed this concept called the Earth Moon Lagrangian point 2, and he called it a halo orbit for the first time. And unfortunately, Apollo 18 was canceled, and his concept was never adopted. Okay, but still, his idea really changed the mind of many things. Okay, saying, "Oh, this is interesting because if you put an object at the halo orbit, the biggest advantage here now, from the communication point of view, is that now you can talk to the future space station continuously, okay? Because it is kind of like going around the moon, on the backside of the moon. So this is really one of the biggest advantages. So you are going behind the moon, and from the Earth, you can continuously communicate with the future station. So this is one big plus. In fact, this was his original motivation to have this station so that we can continuously communicate with the Apollo 18, okay, from this space station here as a relay point. So this is really the whole point when they decided to go for the lunar gateway orbit. So the engineer, the first thing come to their mind is, okay, we have to first, as I said in the second slide, there are two objectives. One is that it will future outposts to go to the lunar surface. That means that the future lunar gateway orbit should be, at some point, should be not too far from the lunar surface, so that like the astronaut can go easily to the lunar surface and easily come back up when they finish the exploration. And also the most important part is this one, delta V. Okay, they have to find an orbit which will require the minimum delta V. I showed earlier when I talked about the equation of delta V, I said that like the delta V, once you know the delta V, then you also have to know the mass of the satellite to know how much fuel it will require. So the heavier the satellite, the more fuel you will require, even for the same delta V. For example, if you say, I need 100 meters per second delta V, if I have a satellite which is like 100 kilograms, and a satellite which is 1 ton, it is not 10 times bigger. Actually, it turned out to be more than 10 times bigger. So this is why delta V, when we're talking about like future space station, like the lunar station, which is still a few tons heavy, even a small delta V can represent a large amount of fuel required to maintain it. So this is the whole motivation when they design the lunar gateway orbit. They have to find the orbit, which first, it should be halo orbit. It should be like have some point very close to the lunar surface, so that it's easy for exploration the lunar surface. And most important driving factor is the delta V. Okay, here this figure shows like different class of like the halo orbit that has been investigated. So the terms are fancy terms. Okay, like the frozen orbit, L2 halo, near rectilinear orbit. This one's a distant retrograde orbit. So don't worry about it. I just want you to focus. At the end of the choice is something we call it linear rectilinear halo orbit. Okay, NRHO. This was the final choice. Okay, near rectilinear halo orbit about Sun, Earth, Moon, Lagrangian point 2. It is of ultimate selective. Okay, and because it is selected because lowest delta requirement to enter from the Earth orbit. So they figure that there's a, as I mentioned, there's a low energy transfer that they can go into it very low energy and very low station keeping cost. I mean, very low delta V and low cost to access the lunar surface. Okay, and most important is the continuous line of sight with the Earth, making a halo around the Moon when viewed from the Earth. So here there are two figures try to explain to you what will it look like. Okay, in this frame here is the Earth-Moon rotating frame. Basically, the Earth and the Moon, they are rotating together. Then the future lunar orbit will look something like this. Okay, it is three-dimensional. You can see this. It is not like a plane. Okay, it gives you a impression it's a plane. Actually, it is not a plane. It is like a kind of like an ellipse which is bent, but some way it is bent around. Okay, so it's a three-dimensional ellipse here. If we look from the point of view from the Moon itself, it will actually, this is what you will see. Okay, from the point of view, if the Moon is here, the future space station will go into different, very funny ellipse. Okay, evolving all the time. Okay, it is not like a constant ellipse. It just keep on moving. Okay, because the orbit is dictated by both the Earth and the Moon, the relative position between the Earth and the Moon, which is not constant. Okay, the Earth and the Moon, the lunar orbit around this, the Earth is like elliptical. Okay, so it is not constant. So this is why the future orbit, the near NRHO orbit, will look something very interesting. Okay, here is an animation to show. Basically, it shows that the period for the future lunar orbit will be roughly about 3,000 kilometers. Okay, at the closest point is about 3,000 kilometers from the lunar surface. At the farthest point is about 71,000 kilometers. The period is about 6.5 days. Okay, keep this in mind. It is not a Keplerian ellipse. Okay, when close orbit, when we're in the Earth Moon rotating frame, this is what I mean. If you look from a frame in which like you assume both the Earth and the Moon moving at the same time, then it looks like a close orbit. But it is not really like that. Okay, this is the animation showing you what it will look like. You can see day 5, day 6, day 7. So roughly it's about 7 days orbit, okay? But it is just not planar. So here I have an animation again to show you like if from the moon, like if the moon is stationary, what will it look like this orbit? Okay, here this like the lunar gateway here. So if you look carefully, so basically it also has the property similar to like Keplerian orbit in the sense that it is at the apollune, so it's going slower. Now as I approach the perilune, it goes faster. All right, it go faster and then go slower again. So it still have the characteristic of a Keplerian orbit, except it is not really a Keplerian ellipse. Okay, it's not too planar. Okay, it is keep on changing shape. The reason is because of the relative position between the sun and the earth keep on changing. So this is why from one orbit to another one, it's not the same shape, but it displays some very interesting property similar to Keplerian orbit. Here I just try using the same animation. I kind of like to do the screen capture for like from starting from here, day 1, day 2, day 3. It's showing you the evolution throughout the orbit here from the point of view from the moon itself. Okay, so you can see it is really not a planar orbit. It is kind of evolving, keep on changing. It looks elliptical, but it's not a closed ellipse. Okay, because it is an ellipse. Keep on changing shape. Okay, so by now I've explained to you now the first point about the bullet saying that future lunar gateway will serve as the outpost for the lunar exploration. The second point say in the bullet there said that the future gateway will also serve as an outpost for like the deep space exploration. What does that mean here? A good example of what does that mean here come from this Chinese mission called Chang'e 2. Okay, it was launched in 2010. So it's a lunar orbiter launched in 2010. At the end of the mission, okay, as I mentioned earlier, at the end of all this lunar mission, the only thing to do is to crash the orbiter on the surface of the moon because you will run out of the delta V, so you cannot maintain orbit. So basically at that time, the Chinese Academy of Science said that, okay, they make a call saying that, scientists tell us where should we crash on the surface of the moon so they can get the last bit of data. However, they received one proposal saying, no, don't crash on the surface of the moon. Let's try to use the last remaining delta V and demonstrate that we can actually use future using like the lunar as a outpost for exploration. Okay, so this is what they said that we can try to demonstrate low energy transfer and use it to explore further. So basically, then they said that use the remaining delta V, turn on the thruster, and push the lunar orbiter into a Sun-Earth Lagrangian point 2. Okay, and then from there, it can make some rendezvous with an asteroid. Okay, so this is what the picture looked like. Okay, so it was originally in the lunar orbit. So at the end, it said, no, don't crash it. So they said use the remaining delta V and using like the low energy transfer. It go into low energy transfer and go into the Sun-Earth Lagrangian point 2 here. Okay, so it's very interesting. So when it's in the Lagrangian point 2 here, then you say that, okay, let's wait for the right moment. Then you can do it like the rendezvous with an asteroid. So this is what it did, do a rendezvous with an asteroid. And so this is how they get the last bit of science out of it. So this is the same concept that like in the future, the lunar gateway. Okay, once you have the lunar gateway there, if we will say, okay, when we have the right moment, we just need very little energy. We can send another probe out into the light to explore other like the asteroid or comet when you fly by near the Earth. Okay, so this is why the future lunar gateway will try to serve two purposes. One is for the lunar surface exploration. The other will be served as like the gateway for future the deep space exploration. So with this conclude my last slide, I believe. So summary, I just want to summarize what I have gone through tonight in 1.5 hours. So I hope you appreciate that. I try to explain to you why Kepler's law is important. Okay. Well, now you understand what the key principle of launcher, why the concept delta is so important. For every space mission to be designed, is really the driving force is always delta V. And I also talk about like Lagrangian orbit, talk about the low energy transfer. So I hope by now you appreciate that when they designed this lunar gateway orbit, it is a really significant technical achievement. Okay, they use all the knowledge, all the experience they have, and come up with something that will be challenging and also would serve a lot of purposes. So with this, I conclude my talk. So we'll take a
Thank you
break.
so much. It was amazing. I'd like us to take 10, are we back at 10 minutes? So we'll take a 10-minute break just to get a quick bio break. Before you leave, there is a raffle that Leslie's running. That beautiful picture up there is up for grabs. So if you are interested, come see Leslie. We're back at 9:43. Okay, tickets are 1 for $2, 3 for $5. Okay, or just ask Leslie. Okay, so we're back in about 10 minutes, Alfred.
Yep.
When we come back, we'll do a Q&A.
Okay.
That's the other thing, where we're going to do a Q&A. And, sorry? Yes, yes. So we'll do a Q&A when we come back. So if you have questions, has a question for our speaker, if anybody has a question for our speaker, come on up and go ahead. I have a question. Okay. Why don't we give Alan the floor and for the first question, and then if you have questions, we would like very much for you to take turns at the mic. Thanks.
I assume it's doctoring, but don't know. Alfred? How about Alfred?
Yeah, Alfred.
My name's
good.
Alan. Okay. My name's Alan. My question is, you talked about low delta V for station keeping in the chosen orbit. Do you have any projections on how that delta V compares to the delta V required for ISS? I know they have to change the orbit to avoid things all the time. I assume you don't have to as often in this lunar orbit. Do you know how it compares?
Oh, it's very significant. The latest number I heard, this one for the lunar gateway, we are talking about less than 10 centimeter per second per year.
Wow.
Okay, per year. Okay, so it is very significant. For the space station, it is very large delta V because it is a low altitude, right? So there's a drag there. So space station, I believe that we are transporting at least about 5 to 7 tons of fuel every year just for station keeping. Okay,
Wow.
and so you cannot afford the same way to transport that much fuel per year for lunar gateway because it costs so much to go all the way there. So this is why this discovery is very significant. I know it is less than 10 centimeter per second per year. This is what they're looking at.
Excellent. Thank you very much.
There's another question coming, Alfred.
Well, Alfred, I just want to make sure I'm understanding this correctly. So the near retrograde orbit, it's going to go around close to the moon's surface at Paraloon, and then is it going to go around the Earth Moon L2 at its apoloon?
Yeah, you can see it. This is always fascinating, right? Because the L2 suppose is about 68,000 kilometers away. So this orbit is, how do I say it? If I show it this way. This is what's fascinating here, okay? The L2 is supposed at the like is very far away. And this orbit will have some kind of properties, like at the closest points about 3,000 or so close to the moon surface. And then the far points are show it correctly. Let me check what's the number I want. So it is at 71,000 kilometers away, okay, the farthest point. But it's still away from the L2. In principle, it is still away from the L2. Okay, this is why this is a like fascinating subject. It is away from the L2, but it is really actually due to the close to the, it's close enough to the L2 that we can discover this class of orbit. Okay, so as I showed earlier, at the L2, Sun F L2, it is roughly 64,000. Okay, 64,000. So this one is really interesting. So kind of like the tail end of the apple is touching the L2. Okay, it's only the tail end of the apple is touching the L2.
Thank you.
Did I explain clearly?
Yes.
That was great. Thank you. There's another question.
Yes.
So my name is Paul Vermaat. Thank you again for that talk. It was really, really interesting. I have a question. I'm still trying to formulate it in my mind. So when the gateway is in this halo orbit, or around the moon, okay,
Yeah.
and you said that it requires very, very little delta V to maintain that orbit, like you were
Yeah.
saying, 10 centimeters per year,
Yeah.
whatever.
Yeah.
What determines that the orbit has degraded? Is it the orbiter itself, or do people on Earth have to figure out that it's degraded and it needs an injection of delta V to maintain it?
Well, of course, like this will be like constantly monitored by the ground station crew, right? So they will make sure. Okay, this is interesting. It takes very little delta V to maintain the orbit, but however, if there is suddenly there's some kind of disturbance for no reason, it can also escape easily from the orbit too. Okay, so this is why it is constantly monitored by the crew. Make sure that there's anything unusual happening. Make sure it stay in the orbit. Okay, so it is not autonomous. It will be really monitored from the ground crew here. They have to like constantly run the simulation, make sure it is staying in what they predict it should be. If there's anything, then they have to really find the delta V to correct it.
Good, thank you.
Any other questions? I have one.
Yes.
So what are the plans for this concept to come to life? And what is the CSA's role in that?
Very good question. My understanding, I don't work directly in the robotics group here. Okay, so my understanding is that they will kind of like first launch all this module, right? Logistic module, power module first. Okay, this should be the first module that will go up, which is the power and propulsion element. That should be the first one to go up. So basically, they try to do like autonomous assembly. Then they'll bring the Canada arm there. Okay, the Canada arm will come in. So really, the Canada contribution is this robotic arm. Okay, this is very critical. They will like use the robotic arm like the way we use in the ISS, try to use it to grab the future module coming in to help them to assemble. to make the task easier for the assembly, and also to try to minimize as much as you can the astronaut EVA, okay? Because it will be much more difficult to do EVA there, right? So they try to reduce the robotic arm as much as we can to minimize the EVA in the future.
Hi, I'm not sure if you covered it, but how long will it take to get the gateway into the orbit that is being proposed? Do you know that number?
Well, when they did the Artemis 1 mission, they released a little CubeSat into this orbit as an experiment. Okay, there was actually an experiment when they released one little CubeSat into this orbit to see how long it does take. Okay, if I remember correctly, it's roughly about a month, somewhere in the range of about a month. The CubeSat is like insert into this orbit, and this is how they kind of like to verify this concept of this like NRHO concept. Okay, so they have some kind of data now. They can verify that yes, that this is interesting. They can really insert into such an orbit.
Okay. And then I was curious, I think you kind of touched on it about the automated assembly. Like a month sounds long to have the astronauts going along in that orbit. So I guess it would be
Yes,
like an automated assembly.
Eventually this will be like habitable. Okay, the whole concept is that it will be habitable when this station is near the perihelion. Then the astronaut can have some way to like, there might be some kind of like another vehicle to drop it onto the lunar surface. Okay, so that when then the astronaut will do the exploration on the lunar surface, when the station come back near the perihelion, then there'll be some way to bring it back up to the space station. This is the whole concept. Yes, it's habitable, but it will not be like right now. You can have 6 astronauts. They don't think they can afford to have 6 astronauts. Again, because like it will take a lot of fuel, a lot of delta V to bring so much supply to such an outpost.
All right, thanks. And last question, I was curious if you knew what the delta V of the ISS is. I don't know if that's it.
Delta V, I know I have to dig up to find out. I know it is very significant because of the drag. It is very low. Okay, I know that they will consume roughly about 5 to 7 tons of fuel a year. Okay, just to maintain the ISS orbit. If you give me a couple minutes, I can show you one slide about the delta V, the fuel requirement.